Hello students, welcome to the online session or the subject of structural analysis. This subject of structural analysis is mainly for the student of structural engineering. Basically, in design of any kind of a structure, first of all analysis is required to be done. If the analysis of the structure is done properly, then the design of the structure can be done properly. So basically, we can say that structural analysis is very important subject for the structural engineering students. So let's start with this important subject of structural analysis. So 3, 2, 1, let's start. Welcome back students to our online session. We have discussed this example in the previous session. It is nothing but an example of a direct and bending stress on which the eccentric load is being acting onto it. The load of this 100 kilonewton is acting onto it. The eccentricity of 40 mm is there, and we have to solve this sum. So we have already started it in the previous session. We have find out its moment of inertia, both of both the members of what the division we have made. Ultimately, we have made the division of the top rectangular section and the bottom vertical rectangular section. Means we have divided the section into two parts: the top flange part and the bottom web part. Okay. So yes, we have find the moment of inertia of it. We have found the centroid of the overall section, that is y bar. Okay, and we have found the section modulus of it. Okay, so the section modulus we are getting is 15724.15 millimeter raised to 3. So this is what the section modulus that we are getting. So now it's time to find the further unknowns, and here the unknowns will be equal to the sigma max, that is the maximum force, maximum shear stress, and sigma minimum, that is the minimum stress. Okay, here our structure is basically a structure on which the eccentric load is acting. If our structure is in such a way that only axial load is acting at the centroidal section, then we can find the stress by just a formula, this P by A. That is nothing but a compressive stress. But over here we are having the load at some eccentricity with respect to the centroidal axis. So because of this eccentricity, the moments can generate. Because of this, the bending stress can also come into the action. By this, the concept of direct and bending stress come into the existence for solving this example. Okay, so let's start with the further. So in the further, you can see over here that we have to find the sigma max. Sigma max will be equal to direct stress plus bending stress. So first of all, let's discuss the direct stress. That is, the formula is F by or P by. Okay, so let's get the value. Here our P that is being given over here is 100 kilonewton, and our area here will be equal to 6700. How? Let's see. We have these two members. So area of the member number 1 is 4000 millimeter square, and area of the member 2 is 2700 millimeter square. So ultimately the area, total area will be equal to the summation of both this area, that is nothing but A2 and plus A1. Okay, so 4000 plus 2700. So by this we are getting the final value of 6700 millimeter square. So this is the why we are taking the area as this one 6700. So we have this load 100 kilonewton by 6700. Now, this was our first term, that is the direct stress, means this one P by. Now, it's time to involve or include the bending stress, means bending stress is nothing but a stress that is being caused because of the eccentric loading. Okay. The previous session, the sessions just before this session, we have discussed the formula to find the bending stress. So, this formula is m by z. Okay. So, m means the moment. So, you can see over here that we have the load of 100 kilonewton at an eccentricity of 40 millimeter. So, the moment that will be causing because of this eccentric loading will be equal to 100 into 10 raised to 3. Thus, we are converting it into the Newton and into the distance, that is 40. So, load is 100 kilonewton, means 1 raised to 100 raised to 3 Newton into the lever arm. The lever arm over here will be 40 mm. So, it will be the moment. Here moment will be equal to 4 into 10 raised to 6 Newton meter. Okay. And we have to divide it by the section modulus. So, we have calculated the section modulus over here, that is section modulus total will be equal to Ixx by y bar. Ixx will be nothing but Ixx1 plus Ixx2, means it is nothing but a summation of both the both the members. So, Ixx1 is also there, which value is 6.629 into 10 raised to 6 millimeter raised to 4 plus Ixx2, that is its value is 16.91 to 10 raised to 6 millimeter raised to 4. Okay, and we have to divide it by the centroidal axis, and that is y bar, that is its value is 149.7 millimeter. By this, we are getting the final value of 157,241.5 millimeter raised to 3, that is millimeter cube. Okay, so yes, in this way we have got the section modulus. So, that will be utilizing it for our calculation. So, by this our equation for the bending stress will be m by z, that will be equal to 4 into 10 raised to 6 divided by 15724.15. So, the value, on solving our first term value that we are getting is 14.92 and the value of our second term is 25.43. Okay. So, by this we are getting the total stress, that is the maximum stress of 40.35 Newton per mm square, and it will be compressive. Okay. So, 40.35 we are getting, and this is the maximum stress. Okay. Just we have utilized all the data that we are given. We have utilized the moment of inertia, we have utilized the section modulus, we have utilized the load into eccentricity for the moment. By this, we are getting this value. Okay. So, this was our maximum stress that is being acting onto our structure when the given condition, given type of condition is given. Okay. In given type of condition, when load is acting, then we will be getting this value. So, this was our maximum stress. Now, it's time for the minimum stress. Okay. So, formula to find the minimum stress will be equal to sigma 0 minus sigma b, means sigma 0 stands for direct stress and sigma b stands for the bending stress. So, we have to subtract the bending stress from the direct stress, and by this we will be getting the minimum stress onto it. So, let us start with its value. So, first of all, we require the direct stress, that is sigma 0. Its formula is just P by A, means load, the axial load that is being acting onto a structure, that is 100 kilonewton. that is 100 kilonewton, and we have the area of 6700 millimeter square. It is nothing but a summation of both the values. Okay, so sigma 0, that is equal to P by A. So it is nothing but this one 100 into 10 raised to 3 divided by 6700. So by this we are getting the value of 14.9. Okay, so this is our direct stress. Now it's time for our bending stress. So bending stress, the formula will be equal to moment by section modulus. So moment that we are getting over here because of the loading that is being acting by the eccentricity of 40 mm will be equal to load into the lever arm, the distance. The load here is 100 into 10 raised to 3 Newton and the eccentricity is of 40 mm. So 1 into 10, 100 into 10 raised to 3 into 40. So we are getting the moment of 4 into 10 raised to 6 Newton into mm, Newton millimeter. Okay, so this was our moment, and the section modulus that we have found in the previous section, that is I by y, that is equal to 15724.15 millimeter is to 3. So we have to try it again. So 4 into 10 raised to 6 divided by 15724.15 will be equal to 25.43. So this is our bending stress. So direct stress minus bending stress, minus, that is 14.92 minus 25.43. So finally we are getting the minimum stress of minus 10.51 Newton per millimeter square. Okay, you can see over here that the minimum stress, our value is negative, and if your value is being negative, sign is negative, then we will be considering it into the tension. Okay, so we can say that its sigma minimum is 10.5. Okay, so that we are getting over. So by this we have found the maximum and the minimum stress. Okay, so yes, this is the thing what we needed. Now one last thing is required over here, that is we need to find out, we have to draw the stress diagram. So stress diagram we need to draw. So here we have drawn it. We can say that at the bottom it will be having the compression, and slowly we are moving towards the top, it will be converting into the tension. So at the bottom we have the compression, and the compression value that we are getting is 40.35 Newton per mm square. Okay, and it is acting at the bottom because it is also positive also, and it will be starting from the bottom, and slowly when we are moving towards the top we will be getting the tension. Okay, so you can see over here that initially it is having a rectangle that is moving on the left hand side, and slowly it's moving towards the neutral axis, and a point will come where it will be changing its characteristics from the compression to the tension. So slowly moving towards the top, somewhere at some height its characteristics is being changing, and finally at the topmost section we are getting the tension. Its tension value is nothing but 10.51. Okay, so whatever the value that we are getting for a tension, we will be putting it over here, and yes, this will be our value for the tension. Okay, so yes, we are getting the tension of 10.51 Newton per mm square at the top, and we will be designating it by the negative sign. You can see over here that at the bottom rectangle section, means bottom diagram. In this diagram, at the bottom triangle we will be having the positive sign, and moving towards the top we will be having the negative sign. This directly represents that at the top we are having the tension, at the bottom we are having the compression. So in this way, we can draw the stress diagram. Okay. So yes, these are the things that is being needed. Let's discuss the steps. Means I just want to summarize the example. What we have to do whenever you get a question like this in an exam. In an exam, what we need to do. So basically, first of all, you have to divide the section into equal parts. Means whatever the division you made, it should be easy for our calculation. So division is required to be done. That will be the step number 1. Step number 2. Here we need to find the centroid for both x-axis also and y-axis also. We have to find the center. Okay, and for that purpose, we need to get the area A1 and the centroid with respect to bottom for all the members. Second step will be we need to find the centroid. Okay, after that, the third step will be the find the moment of inertia with respect to all axes. Means here we are having symmetry along the x-axis, so we have not find it. But yes, if it is necessary, then we need to find. So the third step will be we need to find the moment of inertia. After that, the fourth step will be equal to the section modulus. So we have got the moment of inertia, we have got the centroid, that is y bar. So just we have to divide moment of inertia with y bar, and we will be getting our section modulus. After that, the next step will be we need to, that is the step number I think 6, will be equal to the maximum stress, that is equal to P by A plus M by Z. Okay, and in the last step will be equal, last second step to the 8th step will be equal to the minimum stress, and finally you have to draw the diagram. So this is what the thing that we have. So this is how the example can be solved, and here we are completing the chapter of direct and bending stress. So yes, thank you for attending the session. See you in the next session. So here we are ending our session. Hope you have liked the session. We have discussed each and every topic in brief and also in detail. We have discussed each and every topic's practical application also. So thank you for attending the session, and if you have any kind of a doubt, if you have any kind of a query, then you can send me your doubts and queries in mail. My mail is in my YouTube channel. Do check into my YouTube channel, like it, share it, and again thank you for attending this session. See you in the next session. Thank you.